I'd like to demonstrate aerodynamic lift by radial deflection today, first using DC flow from this ordinary hairdryer, and then using AC flow, alternating current flow, from an audio loudspeaker. This DC flow, or direct current flow, I think you will readily see as I have the hairdryer oriented in a faceplate with a port in the center. When I turn on the fan, there's a clear outward flow. Whereas when we look at the loudspeaker, as I turn up the volume here and hold the ribbon in the port, you'll see it fluttering back and forth, indicating the inward and outward flow characteristic of alternating current. Both will produce lift, however. Now, some people will wonder, how can you get upward lift from a flow which is downward? And for DC flow, I'll be using this thin cardboard wing. There's a thumbtack placed in the center so that I have a little metal post right here. That does nothing to attach the wing to the port in the faceplate, but it does limit the lateral sliding. Because once things are airborne, if I don't hold this perfectly level, the wing will slide right off the experiment. But what happens then is the downward air does build up pressure in the center, and it pushes the wing away. And from a distance, it certainly would. But in close, we have a narrow gap produced. And in that narrow gap, as pressure increases here compared to the atmospheric beyond the wing, particles have a tendency to migrate outward. And those particles which are selected to go outward radially are those which have velocities in a radial direction. And since they have a higher than average velocity in the radial direction, they on average have a lower than average velocity in the up and down direction. So when you have a narrow gap with particles having a higher velocity emerging this way, they have less up and down bouncing this way. Less up and down bouncing means less pressure between the faceplate and the wing compared to ambient air, and therefore the ambient air underneath will push up into the lower pressure of the radially flowing particles. Now, the narrow gap produces passive sorting at the center. But I also think there's active sorting that happens some distance from the gap. That is, particles that were already there, vibrating up and down, get pushed off the edge of the wing by those particles emerging from the high pressure here with the outward velocity. So you clear away those particles that had up and down pressure, and you replace them with particles that have lower up and down pressure because they have a higher outward pressure, radial pressure. And let's put the wing on the scale and take a look from above to see this in action. So now, looking down at our scale from above, I've torn the weight to 0 so that it appears the wing has no weight. When I put the hairdryer current pushing down, you'll see this weight increase like that, a positive number as the air pushes down on the wing. But when I get closer and closer and closer to it, the wing will start to pick up because of the aerodynamic lift, and you'll see this negative sign appear here, showing the weight of the wing as minus 10 grams when it finally picks up. So let's try that. From 0, I'll turn on the fan. You're going to see the weight increase more, and then as we get closer, it goes negative, and we've actually picked up the wing. When I turn the fan off, it falls down again. Let's try that again. I'll replace the wing there, and we're going to bring the fan in from above. The mass increases, then starts to decrease as we get closer, and with lift, we pick up the entire wing, switch off, and it falls down. Let's see that from the side now. So taking a view from in front, here's our wing. we'll pick up the hair dryer and turn the fan on so it pushes down with its flow. You can see it sort of pushing that wing away. We'll come closer. And it picks the wing up. Turn the fan off and it drops. Try it again. Now to demonstrate alternating current flow, I've used a low-frequency driver, and this speaker diaphragm goes up and down, and the sound comes out this port here. Because the flow is going up and down, I can use a much heavier pine wing. That's partly because with DC flow, the air would hit and push down constantly at the center. But with AC flow, it spends half the time pushing down and the other half of the time pulling up, neutralizing that central downforce. And we're left with an oscillating flow across the wing radially in all directions. And for the same reason as before, those particles which have energy in the radial direction have less energy in the vertical direction, and we end up with a decrease in pressure and lift. So let's put that on the scale. And we'll take a view from above. For our acoustic signal, we'll be using a 65 cycle per second sine wave. And we'll be operating at around 50 watts right here, like this. And as we move to the scale pan, we'll see our wing through acoustic streaming, just like with DC flow, start to have an increase in apparent mass. And then pick up the entire wing. All 126 grams of it. And let's see that from in front. Seen from in front, we'll demonstrate lift by radial deflection using AC flow. First, I'll take the power up. And we have lift. Power down, and she drops. Power back up. There's our lift. Power down, and it drops. I call this orthosonic lift by radial deflection because the dimension of the lift, upward, is orthogonal to the two dimensions of radial flow across the upper surface of the wing.